Okay, so okay. So now we're going to the part 2 of this topic on prediction of mass transfer coefficients and design for concentrated mixtures. So actually for part 1, we already covered the prediction of mass transfer coefficients. So part 2 is to talk about the design of an absorption towers for a concentrated mixture. So let's go through the learning outcomes. So we have covered the first two learning outcomes in part 1. So for part 2, we are going to you should be able to calculate the height of a packed towers for absorption and stripping with concentrated mixtures. But the example that I'm going to give in this part is only for absorption, but you can adopt the same process for stripping towers later. Okay, so for absorption of concentrated mixtures in packed towers, so previously the simplified design methods that I have shown you in week 8 and week 9, that is only applicable for absorption of dilute gases in packed towers when the mole fractions of the gas and liquid streams, mole fraction of the solute I mean, in the gas and in liquid streams were less than about 10%. Okay, so if the mole fraction of the solute is less than 10%, then we can obtain straight operating lines and also approximately straight equilibrium lines as well. So that's why we can use the simplified design method. However, in concentrated gas mixture, the operating line and equilibrium line will be substantially curved, and the KYA and KXA primes may vary with the total flow rates. So the design equation must be integrated graphically or numerically because it's not constant. Okay, it is changing throughout the column height. Okay, so a review on the design of equations for the tower height. So these are the equations that you have, may have been familiar with to calculate the tower height based on different phase coefficient, film or overall coefficient. So gas phase film coefficient, you use ky, small kyas and yi. But and then for liquid phase film coefficient, you use small kxa with xi. But if for overall coefficient for gas phase, you use capital Ky, and you instead of using the yi, you use the y star. And for liquid phase, capital K, X, and instead of XI, you use X star. So those are the differences in the design equations to calculate the tower height for absorption and stripping towers. Right, so general steps to follow when we are dealing with concentrated mixtures, it's not as simple as dilute mixtures. Okay, so first step is to obtain equilibrium line and operating line equation. Then after we got those things, we can obtain the KYA and KXA from empirical equations. So these are functions of GY and GX to the power of N or M. So the values of N and M here, the powers of these GX and GY are in the range of 0.2 to 0.8 depending on the empirical equations that you are using. Okay. So using the operating line equation values, we can calculate the total V and L. These are V and L here are the actual vapor and liquid flow rate, not the inert ones. So inert ones are you have the prime, right? V prime and L prime, but this one are the actual ones. Add different values of X and Y in the tower and convert to GY and GX. And then we can use the GY and GX here to calculate the values of KYA and KXA because KYA and KXA are functions of GY and GX. Okay, so if the variation of KYA and KXA at the top and the bottom are small, then an average value can be used. Okay, so these are some preliminary steps. So after we got this preliminary step done, then we start from the tower bottom at point P, P1. So at point P1, the coordinate would be X1 and Y1. So we determine the interface composition M1 if we are using the film coefficient. So we are using interface composition, Xi and Yi. But if you're using the overall coefficient instead of film coefficient, then you're going to use X star and Y star. But just stick with one example for now, yeah? So we are going to use the interface composition xi and yi. Okay, so yeah, you can read this, but you need to know that this is a trial and error process because we don't know what would be the 1 minus xim. So m here meaning the log mean, okay? And 1 is yim. So we use the x1 and y1 first, which we can determine from material balance. So then the values of the first trial, then we can use to calculate the second trial to get the coordinate for M1, the interface composition. So please review this topic on earlier lectures, slides, and videos in lecture 8 or 9. Okay. And then we repeat all the steps for, repeat steps for, because just now we are working on the bottom of the tower, the concentrated end of the tower, pipe absorption. Then we repeat for the dilute end or at the top of the tower, P2, where the coordinate should be x2 and y2. So we got at the top and bottom of the tower now, but we need to also do the same thing for intermediate points in the tower between points P1 and P2. So you may add 2 or 3 more points in the middle between P1 and P2. Okay, so then your goal is to get as many points as possible to actually use the design equation here. Okay, a function of y. This is actually the design equation to calculate the tower height. So we are using gas phase film coefficient in this example. Okay, so the z here is the f of y to do the numerical or graphical integration from y2 to y1, from the top to the bottom of the tower to get the tower height. So this is using gas phase film coefficient. So similarly, the steps are the same if you are using based on other coefficient, let's say liquid phase film coefficient, gas phase overall coefficient, or liquid phase overall coefficient. Let's go through example to better help you to illustrate the problem at hand. Okay, so read the question. A tower packed with 25 mm, 25.4 mm ceramic ring is to be designed to absorb the SO2 from air using pure water. So the solvent is water, solute is SO2, the carrier gas is air at the given temperature and pressure. So the gas entering contains 20 mole% of SO2. So this is a concentrated tower, and that leaving the tower only 2 mole% of SO2. The inert air flow is 6.53 times 10 to the minus 4 kilomole per second. So this is V prime, the inert air flow. And the inert water flow is this kilomole per second. So this is your L prime. The tower diameter is 0.3439 meters. So this one you can use to calculate S, i.e. the cross-sectional area. You can calculate pi d square over 4 to get some area in the unit of meter squared. And you're given the film and mass transfer coefficient at the given temperature and pressure, and temperature especially, this. Okay, so to calculate KYA, this is the correlation as function of GY and GX. Sorry. And to calculate KXA also you're given the correlation. So unit of KYA and KXA are in kilomole per second per meter cube of packing times mole fraction. And the GX and GY are the total liquid and gas flow rates respectively in this unit, okay, kilogram per second per meter squared of the cross-sectional area, which you can calculate here. Okay, so that is what we're going to do, and this is the only question here is to calculate the tower height. Just one thing that you need to do, but a lot of steps that you need to follow. So the first thing is to find the equilibrium data. So this is given in the appendix of the reference book, Jen Coplis. So this equilibrium data is sourced from the literature. So you can try to find out from Industrial and Engineering Chemistry journal, volume, many years ago, very ancient data. However, it doesn't matter. So this is the XA. And I think we are more interested to use YA straight away. So we're gonna use XA and YA at 293 Kelvin, so 20 degrees Celsius. So these are the two columns that we're going to effectively use as the equilibrium data for this problem. Okay, so here I'm just, I already show you the result of calculation, but I'm going to walk you through how to get the table here. So first, let us draw the absorption tower. So you have a tower with inlet air with SO2. So here is your inlet air, air and SO2. And the concentration here is 20% of SO2 and thus 80% of air. And then the outlet air, you want it to contain only, so this is SO2 and air, but with much less SO2. So mole percent here is 2 and 98% of air. And you are using water as the solvent, okay, water and pure water. So so here, if we were to put in terms of X and Y, so this is Y1, so this is 0.1 and this is 0.2. 1 is at the bottom of the tower and 2 is at the top of the tower. So Y1 is 0.20. So here Y2 is 2%, so 0.02. So X2 here is 0 because you don't have any SO2 in the water because we're using pure water. However, the outlet water will have absorbed some SO2 from the incoming air. So you will have some concentration of SO2 in the water outlet. So here you have water plus SO2 absorbed. So this X1 only refers to the concentration of SO2. So here we can find X1 from material balance. So you can use the general equation. So L prime times X2 over 1 minus X2 plus V prime times Y1 over 1 minus Y1. Inlet equals to outlet, right? So equals to L prime times X1 over 1 minus X1 plus V prime times Y2 over 1 minus Y2. Okay. So next we can key in the numbers that we know. So we know from the question L prime is the liquid inert liquid flow rate 4.20 times 10 to the power of minus 2, and X2 is 0, so 0 over 1 minus 0 is actually just 0. And V is 6.53 times 10 to the minus 4, and Y1 is 0.2, the inlet equal to 4.20 again. Okay, here X1 is what you want to find, so we don't know. And V prime is 6.53 times 10 to the minus 4, and Y2 is, you specify it to be 2 more percent, so it's 0.02. Okay, so then you can find X1. Okay, find X1 and you will get X1 equals to 0.00355. So here can go back to your diagram and you know that this is 0.00355. So you have two coordinates for your operating line. So your point 1 is at the bottom of the tower, point 1 is X1 and Y1 is the coordinate would be X1 is 0.00355 and Y1 is 0.20, and your point P2 at the top of the tower is X2 and Y2. So X2 is 0 and Y2 is 0.02. But we need to find some intermediate points. So we need to have a general equation for the operating line. Okay, so we can adapt from here. Okay, we can write down, so we put in the L prime for 4.20 times 10 to the minus 2. So instead of X2 and Y2, we are talking about any point in here. So any X, any Y in the middle of the tower. So we just put X and Y. So X and 1 minus X plus 6.53 times 10 to the minus 4, but this one we keep because this one is Y1 and 1 minus Y1, so we keep it because we need to start from somewhere at some point. So we start from the bottom until somewhere in the middle of the tower, so we maintain the values of Y1 and X1 in the equation. Okay, equal to 4.2 times 10 to the minus 2. Now x1 also we already know, so we put in the value 0.00355 over 1 minus 0.00355 plus the gas flow rate 6.53 times 10 to the minus 4, and instead of x2 y2, so because we are talking about somewhere in the middle of the tower, we just put y and 1 minus y. So this would be your general equation for operating line. Okay, this here is your general equation of the operating line to get some points of x and y somewhere in the middle of the tower. So you need to specify one value to get another value. So let's say you specify y to get x. Okay, so let's specify y. Let's say you put y. Okay, let's see. So here we have y is from 0.2 until 0.02. Okay, this is 0.1 and 0.2. So let's say you put y equals to 0.13, and then you put in this equation, then you will get x equal to 0.00201. Okay, so that is one intermediate point, and then you again you vary as long as the value of y is between 0.02 until 0.20. Okay, it's up to you. You don't have to follow exactly the values inside this slide, but this is an example from the book, so I just follow. Okay, it's easier for me. Okay, so you do some values. I mean, you put some y and then you get some x. You put another y to get some x. So 3 intermediate points that should be sufficient to get some nice curve later. So yeah, you specify the value of y and then you get the value of x. So these are your 3 intermediate points of your absorption tower. Okay, so after you have sorted out the points, the operating line, so then the next thing is to calculate the V and L. So here, V and L here is the actual gas and liquid flow rate, not the, not the V prime. So V prime is what? Is equal to V over 1 minus Y, is it? So you calculate the V, actual V here. Oops. Wait. That is, no. Okay, sorry. Okay. Oh, mana tadi? V inert is V times 1 minus Y. So V is V prime over Y minus Y. So this V prime doesn't change throughout the column because it is the inert flow rate, but the V will change based on the value of Y. So that's why you see that the value of V are changing. So here, this is my Excel file. So the V is always the same here, okay? It is always the same, but you need to calculate what would be the value of V at each of the point from the top to the bottom of the tower. So yeah, you can see here that the formula is this value, the V prime divided by 1 minus the Y. So you get the V's. You do the same thing for L as well. So L prime is 0.042 because it's a 4.2 times 10 to the minus 10 and minus 2, you get that. Then you calculate L, the actual L, not the L prime. Okay, from V and L, you can get the GY and GX because GY and GX are actually gas flow rate and liquid flow rate, but now the unit is in kg per second per meter squared. So you just need to convert. Okay, so let's go through the conversion, but you can work on it on your own later. So after you find out V and L, you can find out GY and GL. Okay, so GY is you can calculate, so from V prime times the molecular weight of air. Okay, my computer is heating up, so that's why it's a bit lagging here. So V plus with V prime times Y over Y minus Y times molecular weight of SO2 divided by the cross-sectional area. You can get the cross-sectional area because you are given in the question the diameter So you calculate the cross-sectional area, you will get 0.0929. So you just use this equation to get the gy, and also similarly you can get gx as well. So for gx, instead of v prime, you use L prime, and instead of molecular weight of air, you use molecular weight of water, and L prime again here. Okay. So instead of y, you use x of SO2 in the water times the molecular weight of SO2, because it's a solid in the water, divided by the same cross-sectional area in meter squared. So you get Gx. So that's where I did it in my Excel file here. So Gx and Gy. Okay, you can see the formula. Okay. So V, I just factorized the V outside lah, but it follows the same process. Okay. Gx as well. And then from Gx and Gy, you can calculate Kya and Kxa. So Kya, you use this, the given correlation here for Kya and the given correlation here for Kxa. So that's why you need to find Gy and Gx first. So just put in the values, okay, into Excel. So these are the part that is easiest lah to do. The trickier part is to calculate the xi and yi, because that is the interface coordinate. Okay, so let's go through the steps just now. Okay, the general steps to follow. This part, the step number 3 is the tricky part, where you need to determine the interface composition M1. So P1 M1, it must have a slope of this. Okay, that's try again with this. I think maybe I'll just add another slide here. So write down on this slide instead of on the whiteboard. Just bear with me. Okay, then after you calculated Kya and Kxa using the equation given, that equation is based on the packings. Okay, then you want to calculate xi and yi at each point. So this is the one that use trial and error. So the slope of the same thing, P1 and M1 is negative k xa prime 1 minus x I m divided by k y a 1 minus y I m, the log mean. I mean it's the same formula that I show you in the steps previously, but because I'm having problem to write it down, wait, minus. This one, okay? So the slope of P1 M1 is this, okay? But now you don't know what is xi, because you have to find the xi. So we start first assuming that 1 minus x1 can be used to as a first trial to replace this 1 minus xim, and 1 minus y1 to replace the 1 minus yim. M is the log mean. So these are the log mean thing. So if you want, you can really go through this and then use that first trial to get what is xim, xi and yi for the first point, xi1 and yi1. Then after you get that, you determine the actual value of xy1 and yi1. So and then you repeat the same step, because you need to work around the gradient. So if you work on the gradient, you will get that the gradient is about negative 15.3. We start at the bottom of the tower, because this is where the inlet of the gas is. Okay, so you start there. You will get that after 2 trials, you will get xi is 0.00565 and yi is 0.1685. And then you repeat the same process to get what are the xi and yi at each intermediate point along the absorption tower. Okay, after that, things would become more straightforward, because why? You just need to go back to the design equation. So this is our design equation if we are using the gas phase film coefficient. So you need to use y and yim. Okay, so here, after you get the yi at each point, then you see you need this 1 minus y. Okay, so you need this 1 minus y. So you calculate 1 minus y at each point. So for example, at the top of the tower, is the y is 0.02, so y minus y is 0.98, and so on. At the bottom of the tower, the y is 0.2, so y minus 0.2 is 0.8. So just drag the formula lah. And then 1 minus yim, this is the log mean. So you just use the formula of log mean and key it in into the Excel. So this is the yi. So you will get these values. And then you also need y minus yi at each point. So this is your y minus yi at each point. It's just the difference between this y here and this y here. Okay, so you'll get these values. So your Fy is V divided by Kya times S. Just follow this. So you just copy at each point what would be your Fy. So this one you can see from my formula there. Okay, formula here. So meaning just put lah. So the V is this, okay, V divided by KYAS. So KYA is this times with S. S is the cross-sectional area, is this, divided by 1 minus YIM, this, green, and then multiply by Y minus Y, is this, multiply by Y minus YI to this. I mean, just plugging in the formula lah at each point. So you have the Fy for this. And then you want to integrate. When you want to calculate the tower height is you integrate from y2 to y1, because y2 is the smallest number, 0.02, y1 is 0.2. So you integrate from 0.02 to 0.20, the Fy dy. So that one you need to plot Fy versus y, because you are integrating with respect to y. So you will get something like this. Okay. So here I'm showing you the chart. So let's say this is your your blue line here is your equilibrium line. You can see that in the beginning it's not straight. It's a bit curved, but towards here it will be more straight. But the operating line is obviously not a straight line, it's slightly curved. That's why you need to have these intermediate points. So the more points you have in the intermediate, the more accurate the curve would be. So 5 points is also sufficient. So this is your P1, X1, Y1 at your bottom of the tower, and P2, X2, Y2 at the top of the tower. So these are the intermediate points. So these are the XI1 and YI1, the interface point, M1 and M2 at the top and the bottom of the tower, and also the intermediate XIs, XI and YI in the intermediate points. So you can plot this you need to plot this to do it, to get the trial and error, because you need to use the gradient. Okay, so you need to use some ruler or something, like manual. Or you can still try to find some analytical trial and error approach instead of graphical, but I leave it to you to explore that. Okay, going back to this table here, so this is Fy and this is your Y. So you plot Fy versus Y. So this is your Fy versus Y. So at 0.2, this is your Fy, and 0.02, this is your Fy, and these are the intermediate. So you integrate this curve graphically or numerically, using whatever numerical methods that you have learned before to get the tower height. So after you integrate, you will get the tower height. The answer is 1.588. So I encourage you to repeat this example on your own using Excel to see if you get a similar or very close enough answer to this. example. Okay, so that's all for absorption. So the next lessons will be on liquid extraction. Thank you.